Facing the high energy use by building chiller systems on campus, on-site thermal storage offers a way to improve the building energy efficiency. Distributed PCM thermal management in building envelopes offers multiple advantages over costly centralized thermal storage. However, conventional PCMs face undesirable heat transfer during the day and uncontrollable heat release back into rooms at night, resulting in poor energy saving. Furthermore, the fixed PCM transition temperature restricts annual utilization to a short period, rendering them unfunctional, or worse than static walls in other seasons. To address these shortcomings, we introduced the Radiative-Assisted Tunable PCM Dynamic Wall, TrPDW, as a smart wall module. During daytime, the TrPDW can absorb the interior heat while blocking heat from the outside with DTI insulation and radiative cooling reflection. At night, by switching the DTI states and radiative emission, it can reject heat to the environment and prevent reheating of the room by the PCM, leveraging free ambient cooling. To actively tune the EC-based PCM, the iodide reaction induced by an applied voltage increases the ion concentration in the TPCM, hence reducing the melting point, allowing it to absorb heat from the room. Reversing the polarity, the ion movement back to the storing chamber raises the melting point, allowing it to release heat to the moderately cool outdoor environment at night with the help of DTIs. The TrPDW uses bistable beams and SMA springs for DTI, which demonstrated a switching ratio of 7.6, with off-state similar to standard insulations. And it requires less than 0.6% of TPCM's latent heat for short activation without continuous input. The DTI is incorporated in our prototype, which has a similar thickness compared with various commercial buildings' insulation layer. The TPCM's transition temperature is tuned by electrodialysis in open air, that changes the concentration of sodium iodide in EC, which are both cheap, hence scalable. This allows a verified temperature swing of 20 degrees with minor change in the TPCM latent heat. The process is highly reversible with no degradation over 40 cycles. The first-generation prototype validated the concept of DTI and TPCM components, and their synergy. The second-generation prototype uses temperature-triggered adaptive thermal control to tune the TrPDW for real-world self-contained application during the diurnal cycle. An Energy Plus simulation of 6 different types of walls was carried out to compare the energy-saving performance of the TrPDW. The results show that TrPDW can save up to 19% energy compared with static walls of the same thickness, thanks to a 7-fold increase in the utilization rate compared with static PCM wall. Our project objectives include optimizing the TrPDW performance, fabricating and validating the multi-module prototype, and testing scaling and deploying the prototype for sustainable on-campus use. The direct benefits for the university include installation into the hydroponic lab, security booths, and warehouses for field demonstrations. The contingency plan involves the use of cascaded PCMs to replace the TPCM to simplify the system and cost. In the long run, we will also pursue collaborations, future fundings, and installation in more buildings for a smart and sustainable future. Thank you.